Good morning, grade 11s. I'm uploading 2 videos today. Now, it's not really a new lesson. It's more just an explanation on how you do certain types of problems, okay, involving specific heat capacity. Now, you might have figured that, some of you, I think, have figured this out without my help, which is great. But yeah, the 2 videos I uploaded today, one is an experiment that I did in my kitchen where I just put a block of metal, or like a weight from the weight room, into a bath of hot water. Okay, and what happened is the hot water cooled down, the metal heated up, and basically I mixed those 2 things together and they reach a final temperature. Okay, so I'm going to explain this to you now, how we do these kinds of problems where you mix things together or you have objects in contact at different temperatures and what happens. We call this the method of mixtures, okay, when we're solving problems this way. I'm just going to read this to you, okay, and I'm going to highlight a few things that I'm writing here. When 2 objects are in thermal contact, okay, heat will transfer from the matter at the higher temperature to the matter at the lower temperature, okay? And this will continue until thermal equilibrium is reached. Now, what that means is that the same final temperature, okay? So, for example, if you have a hot coal or something like that, or a hot, object of some kind, and you throw it in some water, the water will heat up as a result, but that object will cool down, of course, until this will continue until they reach the same temperature, and that's called the equilibrium point when they're at the same temperature, okay? All right, so how do you do problems like this? Well, I'm going to divide my equation into 2 parts here. On the left side of my equation, I have the hotter object that has the higher temperature, right? So this has the higher temperature initially, and this one has the lower temperature initially. And what we're doing is we're putting them into contact, right? So the metal is going to touch the water in this case, in the experiment we did this morning. Now you could have 2 liquids that you mix together at different temperatures. That's basically the same thing, right? Now, before we start, I just want you to recall something. Q is equal to mc delta T, where m is the mass, okay, in kilograms. C is the specific heat capacity in joules per kilogram degrees Celsius or Kelvin, okay, and delta T, T2 minus T1, okay, that's the change in temperature. And again, that's in degrees Celsius or K. It doesn't really matter, okay, which one you use. They're basically the same. They're just shifted by 273 degrees. All right, so now Q lost equals Q gain. Makes sense, right? So in other words, like if I have a bath of hot water that has lost 500 joules of heat, when I put a cold metal into it, well, where do those 500 joules go? Well, they went into the metal, right? And you see what's happening is you're getting a transfer of heat energy, of thermal energy, from one area to another, okay, by conduction. And that's what's happening here. So here, let me show you how this works. I have to put the negative sign in there because if you lose 500 joules, if I put those numbers into the formula here, I'm going to get a negative sign. I'm going to end up with negative 500 joules for the object that's cooled off. But a negative and a positive are not mathematically equal. So I have to put the negative sign there to make sure both sides are positive, okay? And your book does it differently. They say Q lost plus Q gained equals 0, but anyway, you end up getting this. I find this more logical to organize it this way to start with. Okay, and anyway, let's just go ahead and put in the formula. So you get M1C1 delta T1, pardon me, my computer is acting up a little bit this morning, on this side equals M2C2 times delta T2. Now, what are all these subscripts? Well, it's important to realize that these are different substances, right? Like in my experiment this morning, this was water, on that side, and on this other side was metal. So they're not the same object. They don't have the same mass. They don't have the same specific heat capacity, and their temperature changes are different too. So it's important to understand that none of these variables are necessarily the same on either side of the equation. In fact, they're almost always different. So they don't cancel or anything like that. Okay. Now that's basically it. That's the formula that you need. I'm gonna circle this with the rainbow here. This is how you solve method of mixture questions. Okay. So let's do two examples. One example I'm gonna do from the experiment we did this morning. And the second example, we'll do one similar to your assignment, okay? And then that'll be it for today. All right, so let's do the little lab activity that I did. Okay, now I have to figure out, I need my calculator here. I'm just gonna call up a calculator for a second because I measured 2 cups of water, so I need to figure out how much mass of water that is. All right, so a cup is 250 mils. So I had 4 cups of water. So, oh, well, I had a kilogram. Okay, so water. My water, I had M1 equals 1 kilogram of water. Okay, I had T1 equals 64 degrees Celsius in the experiment. Okay, I have T2 equals 51 degrees Celsius. So the water cooled down because I put the cold metal in it, right? And the specific heat capacity of water, I already know it's 4180 joules per kilogram degrees Celsius, okay? Now this was the hotter substance to start with. Now my metal, okay, in the experiment, I know I have M1 was 2.3 kilograms. So it's a 5-pound weight, 2.3 kilograms. It says right on it, okay? T1 for the metal was 21 degrees Celsius. T2 for the metal, they share, notice, they share the same final temperature. That's what happens in method of mixtures, okay? And then finally, what I want to find out in this question is what is the specific heat capacity of that metal? And that's something that we can use to identify it. Now this was the cooler of the 2 substances to start with, starting at the lower temperature, okay? So now all I'm going to do is use my method of mixtures. So, and the goal of this question is this: what is the specific heat capacity of that metal, right? So now all I have to do is use the formula that I wrote down up here and I circled with the rainbow. That's all I have to do. It was very simple, okay? I'm going to go M1. Here, you know what? I might as well, the formula is written right there. So what I'll do is I'll just plug the numbers in, okay? So on the water side, on the hotter side, here, you know what? I'll just do it like this. Water, metal, okay? So on the water side, we got 1 times 4180 times, and I have to put the negative sign there because it's hot, okay? So on the water side, it's hot water. So 1 times 4180 times, pardon me, T2 minus T1 is 51 minus 64, okay, equals, on the metal side here, I have 2.3 times C, okay, that's C for the metal, which I don't know what it is. This should be a C2, pardon me. Everything's a 2 with the metal, right? I don't know why I did that. Let me fix that. I'm sorry, guys. I don't want to redo the video, so just not thinking. Okay, now the T1 and T2 make sense. This is initial and final temperature, but the 2's mean it goes with the metal, okay? Now 2.3 times C2, and it's going to be times 51 minus 21, okay? T2 minus T1 there. There's only one unknown. Okay, so what I'll do is with my calculator, I'll just write at least one step. It doesn't really matter that much. It's pretty straightforward. 51 minus 64 is 13, right? Negative 13. So I'm going to get 4180 times. I get 54,340 on this side. Equals, Okay, that's going to be 30 degrees temperature gained by the metal. Okay, so 2.3 times 30 on that side. 2.3 times 30 is 69. And of course, my variable. Now, it turned into a positive because this was negative. A negative times a negative is a positive. See, both sides have to be positive, okay? And that's why that negative sign is there. All right, so now I'm going to go, it's very straightforward, the algebra here, 5440 divided by 69 equals, I get 787 joules per kilogram degrees Celsius. Now, I mean, my experiment was very crude. Normally you would do it in some kind of insulated container. It's called a calorimeter. I just did it in a plastic cookie container, okay, and so there was lots of heat loss. So that number is probably not very accurate. But you know what? It's the best I could do with what I had here. I just want to show you something. In yesterday's video, okay, I wrote a list of heat capacities. Iron is around 450, okay. Aluminum is around 920. You know, we've got various items here. I'm guessing that our number might be a little bit off, okay. But you could actually go on the list. We got around 700, so maybe the steel is a mixture of iron and nickel. We don't have nickel on the list here, but the alloy of iron and nickel together might have, like, you know, 600, 700 joules per kilogram degrees Celsius. So this is a very limited list. But anyway, there you go. That's how you can sort of identify the specific heat capacity of a substance in a not very precise experiment. But anyway, you get the idea, right? So the purpose of this video is just to explain to you how you would do questions like this. All right, so now I've done one example for you. Okay, now let's do another example from the homework. So actually, I don't want to do one exactly from the homework here. Let me just give you a similar question to one of the homework questions. All right, let's say you have coffee, okay? Let's say your coffee is at 90 degrees Celsius, and then you pour in cream, okay, in there, and I don't know what else you put in coffee, maybe sugar or whatever it is, but the cup is also important, okay? So there is a question like this in the homework. Okay, I'm going to show it to you here. So question number 7 in the homework. Okay, this question here. Now, if you look at it, a ceramic coffee cup, which is typical for these cups that we use, is 116 grams, had a heat capacity of 1,090 joules per kilogram degrees Celsius, is initially at room temperature. You put in a certain amount of cream, okay, and then you also put in the coffee at 80.3 degrees Celsius. So you're mixing all these things together, and they're asking you, what is the final temperature of the system? Okay, the equilibrium temperature of the system is the final temperature of the system. So let's do a similar one, okay? So let's do a similar one. I want you to practice that one. I think you'll find after I do this one, you'll get it, okay? So let's say we do our coffee example, okay, and we do it like this. Let's start with the coffee. We'll say its mass, M1, is, let's make it 300 grams. Let's say its initial temperature is 85 degrees Celsius. Okay, what we're looking for is the final temperature. Okay, it is obviously the hot object, right? Okay, and then its specific heat. Now the question doesn't tell you, but you can assume that the specific heat of coffee is the same as water, okay? And by the way, you can do that all the time. All right, now that's coffee. Now, cream. You take it out of the fridge. You add a couple of tablespoons. Let's say you add 1 tablespoon, so 15 mils, okay? So M2 is 15 grams. By the way, the density of water is 1 gram per mil, okay? T1, you take it out of the fridge, let's say it's at 5 degrees Celsius, okay? T2 again is unknown, and your C for cream again we'll use same as water. Okay, now this is obviously cold. Okay, now your cup, we're not going to ignore the cup, which a lot of these questions will do. Okay, we're going to say M3, okay, is equal to, M3 is equal to, I'm trying to see what's the mass of a cup, 116 grams? Let's make it 200 grams, a little bit bigger. Okay, so we're going to do 300 grams. We're going to say its specific heat is 1090 joules per kilogram degrees Celsius. We're going to say its initial temperature is room temperature. Again, T2 is the one we're looking for. Okay, and yeah, there you go. That's everything. All right, so here, what you're doing is you've got hot coffee at 85 degrees Celsius. You're going to pour it into a cup, and you're also going to add some cream. And that will obviously cool off the coffee, but how much will it cool it off? Okay, is the question. Okay, so here we have all the relevant data that we need. And this time there are two things. Both of these things are cold. Okay, so what we're going to do is we're going to divide it into hot and cold, like this. And we're going to say that the negative Q lost equals the Q gained. Okay, and first this will be, let's say, the cream plus the Q, whoops, capital Q, gained by the cup. Okay, so what's happening is heat is being transferred to both of these things until you reach equilibrium. And so the reason why I picked this question is because I know you're going to ask, because it's not just two things. So you can have more than two things, but it's always the hot object that is losing and the warmer object that's gaining, or sorry, the colder objects that's gaining. And so as long as you sorted out which side of the equation they should be on, then you're good to go. All right, so now let's just plug in all of our values, and we're going to have to leave T2 as an unknown. I'm going to convert all the masses to kilograms. Okay, so on the coffee side, 0.3 times 4180 times, and I'm just going to leave it, I have to put a negative sign, T2, pardon me, T2 minus 85. That's going to equal 0.15 times 4180 times T2 minus 5, and then plus 0.3 times 1090 times T2 minus 20. Okay, now this sort of long equation here is got only one unknown in it, just T2, right? And so what we're trying to solve for is the final equilibrium temperature. Well, that's what T2 is. So they all have the same final equilibrium temperature. So now the rest is algebra, and I'm tempted just to leave it here for you, but what you have to do first is expand all the brackets. So let me show you how you do that. 0.3 times 4180 equals, okay, so here I'm going to get negative 1254 T2 plus, because negative times positive, times 85 equals, that's 106,590, so plus 106,590 equals 0.15 times 4180 equals 627. So you're going to get 627 T2 here minus 3,135. I'm just expanding the brackets, right? No problem. Plus 0.3 times 1090 is 327. So this is 327 T2 minus, and then it's going to be 327 times 20, 6,540. All right, so you have like terms. I'm going to circle them for you or underline them. These three are like terms, and of course the numbers are like terms too. So group your like terms on one side, okay? And then group your numbers on the other side, and then solve for T2. And there's a way you can tell, okay, if you're doing it right. And here, I'm going to finish this one for you just because I'm kind of curious, and I'll show you how you can tell if you're doing it right. Okay, so first I'm going to group my T2s on the right side of the equation. So 627 plus 327, 627 plus 327 plus 1254 equals, so on this side I get, whoops, let's go back to this, 2208 T2, and on the other side I'm going to group all my numbers. So I get 106590 plus 3135 plus 6540 equals, okay, 116265. 116265. Now I'm going to divide both sides by 2208. 208. Okay, and I end up with, divided by 2208, I get 52.65 degrees. So T2 equals 52.66 degrees, I guess I'll round it, degrees C. All right, now I'm going to underline this number. How do I know, get some sense as whether that is correct or not? Okay, well, notice the coffee started at 85. My final temperature, that's the hot object, so my final temperature has to be less than that. And it does meet that criteria, right? So in other words, the hot coffee cooled off. Okay, now the cup and the cream, on the other hand, must warm up. So my final temperature must be higher than 20, which is the temperature of the cup. And that happened also, right? My cold cup at 20 degrees Celsius, it warmed up to 52.66 degrees, okay? And so that's a deal, right? Like, so this is how you do method of mixtures when you have three different things you're mixing together, one thing that's hot and two other things that are cool, okay? And so that's it. That's how you do method of mixtures. It's pretty straightforward. It's just using the formula that I showed you yesterday, and that should allow you to finish the rest of the questions on this assignment, so, and in the homework. So now please finish that one, and that one, okay? So you should be able to do all 7 questions after this, and that's it. All right, guys, so have a good day, and we'll talk to you soon.